Good evening, my dear NEET warriors. Welcome aboard to the NCERT Deep Line by Line series on your Vedantu NEET English channel. And today we are going to do the chapter number 2 of class 12th NCERT Physics. The chapter name is Electrostatic Potential and Capacitance. Chapter 1 was done in 2 parts, if you remember, in the last couple of days. Okay, so get ready with me, your Captain Shreyas, your physics master teacher on the Vedantu NEET English channel. And if you have not yet marked your attendance, that means you are really conjuse people. Yes, hello Paul, hello Krishna, hello Satyashri. Good evening, my dear lovely warriors. Yes, this is your Captain Shreyas and we are continuing our NCERT line by line series so that you are prepared for the final exam, be it boards, be it your NEET. Okay, so let's begin with the class and make sure you are subscribed so that you do not miss any important updates and all the academic content that we give on the channel. At the same time, make sure you are liking the video. Okay, hello Mukunda Das, hello, good evening, my dear students. Let's begin with the lecture. Awesome, let's begin. So, in this particular chapter, like the name suggests, it's all about discussing potential energies, electric potential, and then also calculating the potential or the energies due to different systems like a charge or a sphere, dipole, etc. And then finally we go to capacitance, which is an energy storing device. That's why it is included in this chapter. So capacitor stores electrical energy. So we'll be seeing how to calculate the capacitance and what is a capacitor, how much energy does it store, and can you combine capacitors to find the equivalent. Okay, so these are the topics that are there basically in this particular chapter. So let's start with the introduction. Hello Sampath, hello Rishmita, hello Chitra, good evening. Thank you for all the fire and all the warmth that you guys give. Hello Harborain, good evening. In this particular paragraph, we basically define or we recollect what was energy. We define and recollect what was mechanical energy and the concept of conservative forces. So let's have a look at it. I will mark the important lines and then I'll start explaining them also. When an external force does work from one point to another against a force like spring, etc., that work gets stored as potential energy of the body. When external force is removed, the body moves, gaining back the kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energy is conserved. Forces of this kind are called as conservative forces. Spring, gravitation are examples of conservative forces. So here they talk about something called as the conservative force. We'll talk about it. Spring and gravitational forces are examples of conservative forces, and these conservative forces ensure that the sum of kinetic energies and potential energies is always going to be conserved. That's why conservative. And what is the meaning of potential energy? Energy which is stored because of the manner in which it has been configured, the situation, the arrangement, the manner in which it has been placed. The energy which is stored in that form because of its configuration is called as potential energy. So we'll discuss what these initial lines mean in a bit. Coulomb's force between charges is also conservative. Even Coulomb's force, that means electric force between two charges, is also conservative force. That is what it is mentioned. This is not surprising since both of them have inverse square law dependence. Thus, the potential energy of a mass in the gravitational field, we can define electric potential energy in electric field. Okay. What they mean over here is that just like gravitational force has a law G m1 m2 by r square, electric force also has a law Coulomb's constant q1 q2 by r square. So if gravitational force was conservative, even electric force is conservative. Now let's understand what is the meaning of this conservative force. I'll explain this entire thing now. Okay, I just marked some important lines over here. See, imagine, say for example, there is a box over here. You have given it certain speed. And this particular surface is basically rough. So what do you think will this box do when the box is left on this rough surface with certain speed? Yep, what do you think will happen? Yes, it will lose its kinetic energy, it will lose its speed, and eventually you will see that this box will eventually stop. It will move, 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 and eventually it will stop after some time, after traveling some distance. If you notice, over here, it had some kinetic energy. At this particular point, the kinetic energy became zero. Potential wise, gravitation wise, it did not change anything because it was at the same horizontal level. So I would say that whatever potential energy it had initially, it has the same potential energy finally, gravitation wise. Now if I add both of them, if I add both these things, if I add both the kinetic and the potential energy, the total energy which I get is called as the mechanical energy. It is called as the mechanical energy. There is some mechanical energy before. If I add both of them, I will get the mechanical energy later on. The sum of kinetic and potential is called as mechanical energy. So mechanical energy is kinetic energy plus potential energy. This is something which you should definitely know. Now, if you notice, since the kinetic energy vanished, don't you agree that the final mechanical energy is less than the original mechanical energy? Don't you see the mechanical energy has become less as compared to before? That means, can I say that there is 100% loss of mechanical energy? Loss of mechanical energy, or else I can say mechanical energy is not conserved. Mechanical energy is basically not conserved. It is not constant. Why is it not conserved? Is because of friction. Because there is friction. So examples are friction, drag force, viscous force, normal, tension, etc. are said to be non-conservative forces. Non-conservative forces because they do not let the mechanical energy to be conserved. Did you understand the meaning of non-conservative forces? These are evil forces. These are basically evil forces. These are basically evil forces. Understand that. Okay? These are basically evil forces. These are basically evil forces. They suck out the energy from the system. Air resistance force, frictional force. When you move two fluids together, there is some turbulence, there is some fluid friction, which is called as viscous force. All these are non-conservative in nature. But there are some good forces also. There are some good forces also, and those forces are said to be conservative in nature. Say for example, you drop a ball, okay, you drop a ball from some height, you will see it will go down, and after some time, assuming there is no air resistance, this ball will gain some kinetic energy. Yes. So where does this kinetic energy come from? It comes from the potential energy. So the potential energy converts itself into kinetic energy. Earlier, what would happen that the kinetic energy will be zero. After this point, after reaching this point, let's say the potential energy becomes zero. So you can see the potential plus kinetic, kinetic plus potential, sum will be conserved because the potential just got converted over here. So if you add them up, the mechanical energy which is there initially will be numerically equal to the mechanical energy finally. Hence, I would say that the mechanical energy is conserved, and there is no loss, and there are examples of such forces. Such forces are said to be what? Conservative forces. Conservative forces. Which are the examples of conservative forces? They have given over here. Spring, gravity, okay, electric force. These are examples of conservative. You stretch a spring, leave it, energy is conserved. Spring energy gets converted into kinetic. You leave a ball from the top, potential energy gets converted into kinetic. You throw a ball from below, kinetic gets stored as potential. You take two charges which repel each other, they don't like each other. You leave them, they will start going away. So their electrical potential energy gets converted into kinetic energy. You take a proton and leave it towards the electron. You will see that the proton gets accelerated towards the electron because of attraction. So the electrical potential energy gets converted into the kinetic energy. So mechanical energy is conserved because of Coulomb force, spring force, gravitational force, which are said to be conservative in nature. That is what is explained in the first page or the 2.1 introduction. Is this point clear? Absolutely. Did you understand this particular paragraph? Everyone? Yep. Okay. Now, what they mention also over here is very important. What they mention over here is also very important. When an external force does work in taking a body from a point to another point against a force like spring or gravitation, that work gets stored as potential energy of the body. This is where they basically talk about how we define the potential energy. In fact, let me put it right over here. Say for example, there is a ball over here. There is a ball over here. I take it somewhere and I finally place it over here along this path, along this particular path. Now see, what is this line telling you? And an external force does work in taking a body from one point to another against a force like spring or gravity. That work gets stored as potential energy. Think about it. When I take this ball from here to here, I'll be doing some work, right? I have to lift this ball, I have to lift this book, I have to lift this object. So maybe, example, the external force does 7 joules of work. Where will this work go? Is it vanished? Is it taken away? Is it lost to the surroundings? Is it converted into heat? Is it never going to come back to me? No. This exact work gets stored as potential energy. So I will say that as compared to this, there is an extra potential energy. Generally, the symbol for potential energy is capital U, okay? Energy, potential energy is capital U. You can also use, in school days, you used to use PE. PE doesn't look good because if I write PE, people might get confused. Is it dipole moment into electric field, right? So it looks little confusing. If I write K into E, this might look very different. Coulomb's constant into electric field, or it could mean something else. So that's why we usually avoid such kind of writing. We use the symbol capital U. So the extra potential energy that will get stored in it, is basically 7 joules. Similarly, imagine that there is a spring over here and somebody compresses the spring. Somebody compresses that spring and ends up doing 12 joules of work. This is the work done externally by some external force. I am a Pandu who is trying to push that spring. I ate a vada pav, I ate vada sambar, and my vada sambar energy was 12 joules and it got stored over here. So that potential energy stored in the spring will be basically 12 joules. Same way I can talk about, imagine there is a proton and imagine there is another proton over here. They are separated by some distance. This proton hits this proton hits this. But assume that this proton can't move, but somehow I bring this proton here. In this process, obviously, I have done some work. Maybe I did 2 joules of work. So there is an increase of the potential energy by 2 joules. That is what has been explained in this particular initial line. Is this clear? I hope you are loving the NCERT decoding sessions where we are going deep into NCERT. Yeah, and if you are loving it, make sure you are smashing the like button in case you have forgotten it. Great. Now let's move ahead and see what is there ahead. Consider an electric field due to some charge. For simplicity, consider the field due to a point charge. Now imagine we bring a test charge at a point. Imagine we bring a test charge Q from a point R to a point P. So there is already a charge capital Q. You are bringing a test charge small q from point R to point P against the repulsive force between these two charges with reference to this figure. Since both are positive or both are negative, assuming for this particular example, there are two remarks which we can make. First, we assume that the test charge, which is this one, is so small that it does not disturb the original charge, which kind of makes sense, because if this charge was significant, if it is not a test charge, then it will start pushing this away. Imagine your mom has made some nice food, whatever, maybe some nice sambar, okay, a nice sambar, okay, your mom has made some nice sambar, and your mom is not so sure whether that sambar is nice or not. Imagine your mom takes one big bowl of big empty bowl, she dips it in that sambar vessel, and she takes it and she drinks it, and she's like, there is less salt, I need to put more salt. We're like, what are you doing, mom? Please, you finish the sambar, what will you put now? So obviously, when you have to check whether things are all right or not, what you do? You just basically take your finger and just lick it and say, okay, the salt is less or the spiciness is more, and then you add accordingly, right? So whenever you have to test, you do not suck out the entire thing. When you have to do blood test, you do not take out the entire blood from the person, then the person will die. So you take out a small sample. Same way, this test charge has to be really small so that it does not affect this charge. Then what are you testing? So that is one thing. So first we assume that the test charge is so small that it does not disturb the original configuration, basically the charge Q at the origin, or else things will change, number one. Okay, second point, this was the first point. This was the first point. The second point is over here. The second point is over here. Okay, where if you are moving this test charge from this point to this point, you have to apply an external force or else it won't move, because these two people hate each other. Remember, there is a repulsive force between them. This charge gets repelled by this charge. There is 100% some repulsion between them because they are like charges. That's what I have assumed. So you need to push them so that it can, the external force, this is electric force. The electric force will be here, whereas the external force will be exactly in this direction. External force, F external, will be in this direction. So the external force is just enough to counter the repulsive force, is just enough to counter the repulsive electric force, so that you will be able to bring this charge from here to here. If it is not, you cannot bring that charge. Whatever repulsion you are experiencing, you have to counter it, only then you can bring it. That is what it is saying. This means there is no net force or acceleration on the charge. When it is brought, it's fine. So you are bringing it very slowly. I think you have heard this word for a process which happens very slowly, especially in chemistry, thermodynamics. What is that word, guys? Imagine you see a person slowly going from one place to another, like this, going like this, like this. See, even I am moving right now. Maybe you can't see me moving so much, but I am moving, guys. If you wait for 2-3 years, now I am doing it really fast actually, maybe I will move from one place to another. So this is such a slow process. See, I am slowly moving. This is called as a quasi-static process. Static process. Agree or disagree, everyone with me? Understood? What is the meaning of quasi-static process? It's a very, very slow process. So in such a process, which is basically quasi-static, it's slow, very, very slow. So there is no net force or acceleration of the charge. There is no net force or the acceleration of the charge. That means it is brought in very, very slowly at a constant speed. In this situation, the work done by the force is negative, very, very important. External force. The work done by the external force is negative. Is it true? Let's check this out. Work done by the external force is the negative of the work done by the electric force. is negative of the work, done by the electric force. See if it makes sense. If electric force, example, if work done by electric force, if you see, it is opposite to the displacement, example, it is minus 8 joules, then the work done by external force will be exactly 8 joules, because only the direction of the forces are opposite, displacements are same. Same displacement but opposite directions, so they will be negative of each other. That is what they are saying. The work done by external force is negative of the work done by electric force, correct? And this particular work done by the external force gets fully stored in the form of potential energy of the charge. Exactly. So there will be an increase in the potential energy. Whatever work I do externally will get stored in the form of potential energy. So increase in the potential energy will be 8 joules. That's what it says. Agree or disagree? Did you understand it with this example? I am pushing this charge. I am doing 8 joules of work. Whatever work I do will get stored in the charge system, and that increase in the potential energy which is stored is 8 joules. Same time, you can also look at it. Electric force is doing negative work, meaning it is bad. It's taking away my energy. Whatever work I do, I did 8 joules, it is taking. But don't worry, if it is taking, it is storing. Remember, electric force is conservative. It is like that good friend of yours. Remember, if you might have seen practically also, if you give money to some friend, hey, listen, I can't keep this money right now. I don't have pockets. You just keep it with you. Okay. After 1 hour, if you ask the friend, he will be like, okay, take back the money. So electric force is that. So even if electric force is doing negative work, it is storing it over here. But friction is not like that. There are some friends where you give money. Hey, listen, keep the money. I don't have pockets. Okay. After 1 hour, what money? I don't know. Non-conservative, evil force. Got it? So electric force might be doing negative work, but don't get scared. It is storing it faithfully. Yes. Naresh, I am doing it for all the chapters. No, bacha. We started off with chapter 1, chapter 2, chapter 3. But that will only happen if you show your full support, full energy. Everybody should attend it with full energy, with full comments, full josh, full attentiveness, full likes. Yes, only then. Yeah? Correct. Awesome. Let's move on. So that is what is said. If the external force is removed on reaching point P, then the force will take charge Q from the, and is used to provide kinetic energy. This kind of makes sense. Just imagine, this charge is capital Q. This charge is your test charge. This capital Q does not move because this is very small. Slowly, I bring it over here. So potential energy is 100% stored now, is stored in it now. And now imagine what I do is I basically release it. I basically release this particular charge small q. What will happen is you will notice that this charge will begin to move. It will accelerate. Kinetic energy will be gained. Where is this kinetic energy gaining from? This is being gained at the loss of the electrical potential energy. So it will start gaining kinetic energy because it is losing the potential energy, and thus energy is conserved. That is what is explained in the last thing, which is very obvious, nothing to remember as such, but that's why I'm not underlining it. Okay, well, this is explained in the next slide. So this particular part, check the next slide. Is that okay, everyone? Clear till this point? Shall we go ahead? Very good. Awesomeness. Let's move on. Now here I think they have mistook something over here. I'll tell you what this is. There's a work done again, electric force and stored as potential energy at every point in the electric field. Charge possesses a certain electric potential energy. This work done increases the potential energy, blah blah blah. Thus the potential energy difference is blah blah blah. Note here displacement is opposite to the electric force, and hence the work done by electric force is negative. Therefore we can define electric potential energy difference and all these things. Okay. So this is one important formula. Okay. Particle possesses certain, there's a work done Thus the work done by the external forces increases the potential energy by an amount equal to the potential energy difference between the points R and P. Okay. Okay. So work done by electric field is negative. Yes, we saw that right over here. So work done by that repulsive electric field, work done by electric field is negative. Okay. Therefore, we can define electric potential energy difference between 2 points of the work done to blah blah blah. Okay. So I'll tell you what this is. It's exactly that same example what I gave you over here. It's exactly that same example what I gave you over here. See, imagine there is this charge, test charge over here, okay, and I slowly quasi-statically bring it over here, and this was the initial position, this is the final position. In this process, what will happen is my external force is this way, whereas the internal force or the electric force is exactly opposite way. This is the electric force. Everybody agrees till this point? Okay. They are direction wise opposite, magnitude wise same. Now, whatever will be the gain in the potential energy, which is basically delta U, will be exactly equal to the work done by our external force. This is something which you have seen here also. Whatever work you do is the increase in the potential energy. Which is work done by our external force. At the same time, what happens is the electric force does exactly negative amount of work. So this is minus work done by our electrical force. Is that clear? Because that is exactly what I have written over here. If this is positive, this will be negative. If this was positive, these two will be negative. So this is what exactly has been explained on that slide in a very complex manner. First they put in active voice, then they put in passive voice, then they mention one line, then they mention other line, then they mention second line, then they mention one line. So it looks very confusing. I have decoded it for you in very simple manner. Yep. We'll come to that. We'll come from infinity to that point in a bit. Hold on. First, let's understand these definitions first. So I hope this much part is clear. And whenever you talk about work, what is it? If you are moving it slowly from one point to the another, how do you calculate the work? You integrate the force with respect to displacement. So force dot displacement. So this force will be also external force. Dot product force dot displacement is basically integration is the work done's definition. That's how you calculate it. In this particular scenario, the work done by the force is external force is positive because displacement and the force are in the same direction. But had you written it down for, so in this case, this will be just positive F external into displacement. But had you done this for, you know, what do you say? What is that? Electric force, this will be exactly negative. So this will be negative of F electric dot dr. Remember, this negative sign has come from here, all right? And the electric force will be exactly doing negative work. So when you write for electric force, this negative sign will come. Don't worry about it so much. If you just remember, work is force dot displacement's integration, which you have studied in 11th standard. It is very obvious. You don't have to memorize this separately. Only thing you learned new is electric force and external force do opposite sign of work. That is the main takeaway. From this entire paragraph. That's all. Is that okay? And when I say delta U, what is delta U means? Final minus initial. Always change means final minus initial. That's what it means. Now, there are two new things that are commented at this particular point of time. So what are those two things after this particular paragraph? Let's have a look. The right side of the equation depends only on the initial and final positions, meaning what is the right side? That is basically this one. basically the integration part. That's what they are mentioning. Okay, it means the work done by electric field from one point to the other depends only on the initial and final positions and is independent of the path taken. This is a fundamental characteristic of conservative force. The concept of potential energy would not be meaningful if the work dependent on the path. The path independence of work defined by electric field can be proved using Coulomb's law. We omit this proof here. Okay, the proof is not needed. So what is the most important thing over here? Observe this carefully. So they talk about basically conservative forces. So about a conservative force, there is a very important fundamental characteristic. And what is that characteristic? It is that the work done by electric forces or spring force or gravitational force, which are conservative in nature, to go from one point to another, depends only on the initial and the final locations, and it is independent of what? The path which is being taken to go from one point to the other. Very, very interesting thing. It makes sense. See, if I take a mass and move it like this and take it here, versus I take that same mass and I take it like this and bring it here, okay, versus this, if this took 5 joules of work, then this will also take 5 joules of work. As long as origin and destination is the same, path does not matter. Such a force is conservative. In fact, that is a property of a conservative force. Same thing also applies for electric force. Over here, it doesn't matter whether I come like this or whether I come like this or whether I go like this and then come over here. Doesn't matter, as long as my origin and the final locations remain the same. How I reach it does not matter. That is the meaning of conservative force. That is what they mention over here. Is this point clear? Absolutely understood conservative force? Very good. Now, the next important point they mention over here is defines the potential energy difference in terms of physical meaningful quantity work. This equation which is there, whatever this equation which is there, it defines whatever I have written over here. It defines the definition of the change of the potential energy in terms of the work. So you can see energy difference is defined in terms of work. Okay, very interesting. So let's block it over here. So potential energy difference is defined in terms of physically meaningful quantity, which is basically work. So potential energy difference is in terms of work. Clearly, potential energy so defined is undetermined to within an additive consistent. What is means is actual value of potential energy is not physically significant. It is only the difference of the potential energy that is significant. We can always arbitrarily choose any constant and this will not change the potential energy difference. And put it differently, there is a freedom in choosing a point where the potential energy is zero. A convenient choice is to have electric potential energy zero at infinity. With this choice, we take R at infinity, we get this equation. Okay, say what it means. Observe this carefully. Imagine you are taking some charge from here to here. Path does not really matter as long as my initial and final points are the same. Imagine there is one Pandu who says at this point the initial potential energy is example 7 joules. That Pandu says final potential energy at this particular point example is 10 joules. Okay, here it was 7 joules, here it is 10 joules. Another Pandu says no. At this particular point the initial potential energy was actually 2 joules and here the potential energy finally was basically 5 joules. Which Pandu was correct? The pink one or the blue one? The answer is both are right. It doesn't really matter. Why? This Pandu has taken this point as 2, this point as 7. This Pandu has taken this point as 7. What is same in both of them is the difference of the potential energy. 10 minus 7 is 3, 5 minus 2 is 3. Doesn't really matter as long as the difference is the same. So you can arbitrarily choose anything as 0. This Pandu has chosen something else as 0. This Pandu has chosen something else as his 0 reference. So somebody might say, for me, at this particular point, the initial potential energy is 0. So in that case, the final potential energy in this situation will be 3 joules. Somebody else might say, no, for me, here the potential energy is minus 3 joules. Then for them, this final energy will be 0 joules. Every time the difference is the same. That is what is the meaning of this second point. Is that the actual value of the potential energy is not physically significant. Very, very important. The actual value of the potential energy is not significant. It is only the difference. It is only the difference of energy that is significant. What you choose as 0 does not matter. The difference in everything is always the same. You saw that. The difference of the potential energy every time was 3 joules. That's what matters, because the difference only converts into kinetic energy. If the potential energy changed by 3 joules, kinetic energy would have also changed by 3 joules to keep the energy conserved. Is that clear? Everybody with me understood this paragraph? I hope you are seeing NCERT through a new lens, through new eyes, never like before, especially in English medium. In fact, even in other languages, I don't see many NCERT videos. Yeah. So recently, people have started to realize that, listen, NCERT is important. You cannot ignore. NTA takes NCERT as the guiding force to design its question paper. Directly questions are asked, and it has around 50% plus weightage in your NEET preparation overall. Now, put it differently, there is a freedom of choosing the point. Yes, correct. I had the freedom of choosing what I take as 0 perfectly. And a convenient choice is to have electric energy as 0 at infinity. This is very, very, very important. The convenient choice is to have electrical potential energy which is 0 at infinity, because there are so many choices available. Usually we take infinite separation. The charges are so far. Imagine one charge is here, other charge is lakhs and lakhs and lakhs and lakhs and crores of kilometers away. That charge doesn't even know that charge is there. So they are so far, they do not affect each other much. And then I say, okay, now you are at 0 potential energy. That is why we have defined 0 potential energy at infinity, at basically infinity. I hope this is absolutely clear. Since the point P is arbitrary, provides the definition of potential energy of a charge. So finally we get the formal definition of potential energy. The definition of potential energy of a charge Q at any point. So what is that definition going to be? The potential energy of a charge Q at any point in the presence of field blah 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 is the work done by the external force, okay, in bringing the charge Q from infinity to that point. So what this means is that, I'll tell you, explain this to you, observe this. The end of the universe is here. This is infinity. The end of the universe is here. Okay. And my test charge which was there, slowly I bring it from infinity like this, and I bring it over here. So I have brought my test charge over here finally. So this is where my final test charge is, and my other capital Q charge is over here at this particular point. So this final location from this initial location, this particular point, they have labeled it as P. Don't worry about it. Now remember, just some time back I had told you this definition. Change of the potential energy is the work done by the external force. Work done by the external force. So here also I can say that the change of the potential energy is nothing but the work done by that external force. Is the work done basically from the external force. Now in the older case, it was from initial to the final point. What is delta U? It is nothing but U final minus initial. Final minus initial is delta U. So it is work done by the external in bringing it from initial point to the final point. In this case, where is my initial point? Where is my initial point? It is at infinity. Where is it? It is at infinity. So if the initial point is basically at infinity, so I'll put u infinity over here as it is, observe it carefully. So it is nothing but work done by the external force to bring it from infinity to our final location. From infinity to our final location. But what did I just define? What did I just define energy at infinity as? I just told the potential energy at infinity, U infinity. What is it? It is 0. I've assumed it as reference. So this is 0, my dear warriors. This is 0, my dear warriors. Hence, I will get the final answer. So UF minus U infinity, which is 0, is work done by external force to bring it from infinity to that particular point. So hence, the energy at that particular point is the work done by external force to bring it from infinity to our final location. From infinity to our final location. That is the definition of potential energy now. That now becomes the definition of potential energy at a point. Potential energy at any point is the work done to bring the charge from infinity to that particular final location. Is this clear? I hope this decoding was necessary for you to understand what is happening here. Got it, everyone? Absolutely clear? Pakka? All the warrior pandus, whistle podu. Okay, take your moment to understand this particular page. Here I have written F, here they have written P. I have written F, they have written P. That's the only difference. Great. Let's move ahead. So energy is done. Energy is done. I think they have not mentioned, but I will tell you over here. This formula which comes for two charges separated by some distance. This potential energy between two charges comes out as Coulomb's constant, charge 1, charge 2 divided by R square. Charge 1, charge 2, divided by R, my bad. So this is the potential energy between two charges. This is electrical potential energy between two charges as shown. Okay, the separation between them is R. Now please remember, potential energy can be, it can be positive and it can also be negative. Can you guess when will it be positive? It will be positive if both are multiplying to give a positive number. That means one is positive, other is also positive, or one is negative, other is also negative. Negative into negative is also positive. It will be negative potential energy if one is positive, one is negative. Basically, one negative, one positive, unlike charges, will give you negative potential energy. So don't think potential energy is always positive, electrical. It can be positive also, it can be negative also, depending on the sign of the charges. Thank you, Malsa. I'm not sure how to pronounce your name. I don't want to pronounce it wrong. Thank you for all the love from Mizoram. Thank you so much, my dear. Thank you so much, my dear. Now, next comes the concept of electrical potential. You might be wondering, fine, formula wise, sir, maybe I will understand, but why this new term? Will come to it. It's just like why we needed field when we had a force. Force is between two charges, but field is produced even by a single charge. Every charge produces a field around it. When you have two charges or more charges, they experience force. Same way, whenever you have two or three charges, they have energy of the system. But when you have a single charge, it produces a potential around it, just like it produces field around it. It does not have energy, but it has potential. Another way of Simply putting it, another way of simply putting it, by the way, the symbol of electrical potential is V, okay, is basically V. If you ask me, every NEET aspirant right now has potential. Everybody has that potential to score 700 plus. If you study well, if you attend the classes sincerely, if you are very regular, 100% you can score really well. You have the potential. When you get your result, when you get your NEET result, when you seek the admission in AIMS, that's when you have got the energy, when you have taken admission in AIMS. Understand that. Isn't it right? Thank you for all the love from Tamil Nadu. Thank you so much, Krishna. Thank you so much, Rutu. Yep. So same way, even a single charge has an electric potential around it. When you place other charges, it gains energy. But the way in which we define it is not so simple. We have to define it mathematically or properly. So this was just for your understanding purposes. So consider any general charge. We define potential energy of a test charge in terms of work done. This work done obviously is proportional to Q, since the force at any point is QE, where E is the field. It is therefore convenient to divide the work by the amount of charge so that the resulting quantity is independent of Q. In other words, the work done per unit test charge is the characteristic of the field with the charge. This leads to the idea of potential due to a charge configuration. So the work done by external force in bringing a unit positive charge from point R to point P is basically the potential difference, where Vp and Vp are the potentials at respective points. Note, as before, it is not the actual value of potential but the potential difference which is significant. Therefore, we choose potential to be 0 at infinity. The work done by external force in bringing unit positive charge from infinity to point P is the electric potential at that particular point. Okay, so what are the important things over here? First of all, this one, the work done by an external force in bringing a unit positive charge from infinity to that point is the electric potential at that particular point. Number 2, the work done in bringing the unit charge from point R to point P is the potential difference between these 2 points, which is energy difference by charge Q. This is another important line. Also, in other words, work done per unit test charge is the characteristic of the electric field associated with the charge configuration. This leads to the idea of something called as electrical potential due to a given charge configuration. Okay. In other words, electric potential, don't worry, I will explain everything. First, I am marking all the important lines over here. The electric potential at any point in a region with electric field is the work done. Again, the same thing. See, I told you, right? NCERT is pro at that. They keep on repeating the same thing. It's like, I think there are those students, they don't know the answers for a question, and the question is worth 5 marks. So explain whatever. Explain seasons on earth. The seasons on earth are very good. The seasons are summer, winter, rainy season. But first season in the year is, this rainy season comes, then whatever, summer comes, then rainy season comes, then winter comes. The last season is winter. After rainy season comes winter, and then the cycles of seasons are very good, blah, blah, blah. They keep on repeating and fill up the page. So I feel they have done very similar things. The qualifying remarks made earlier regarding potential energy also apply the definition of potential to obtain the work done per unit test. See, again, work done per unit test charge. We should take infinitely small test charge to obtain the work done in bringing from infinity to the point P. How many times will you say the same thing? Infinity to the point per unit charge. Also, the external force at every point of the path is to be equal and opposite. Okay. Right. So let me explain this all to you in very simple words. No hitting around the bush. No hitting around the bush. Okay. Let's learn this properly. Thank you for all the love, Paul AG from Andhra Pradesh. All right. So here is how it goes. See, earlier we had some Q charge. This was our beautiful test charge which came from some point to some point. This was initial, this was final. All this happened because of some external force. Okay, great. And maybe, example, let's take examples, guys. So maybe the work done by our external force, who knows, maybe it is 20 joules, example. This test charge, just chumma I'm putting something, let's say it is 2 coulombs, okay, or let's say it is 4 coulombs. I know it is very big, this is just for you to understand. Now, I got 4 coulombs charge from some point to some point, the work done was 20 joules. If I ask you, per unit charge, per unit test charge, how much work will be done? So say for example, I change the situation now. I tell you, I am bringing a unit charge from here to here. I am bringing a unit charge from here to here. What is that work done per unit charge, per unit test charge, per unit test charge? The answer will be, okay, I took 20 joules per 4 coulombs. So per coulomb, it will be 5 joules per coulomb. That is basically called as 5 volts. So in fact, that is how the definition of volts come. Voltage is a unit of something called as potential. This work done per unit test charge is also basically the potential difference. Just like this work done was giving me potential energy difference, right? This was potential energy difference. This work done per unit test charge from one point to another gives you potential difference. Potential difference, not energy. Remember this. This is not just potential energy. This is just potential. This is potential energy difference. So when you divide it per coulomb, what you get is potential difference. Is that clear? So we also define what volts is over here at this particular point of time, or rather I'll put it on the next slide. 1 volt is when 1 joule of work is done per 1 coulomb. Per coulomb. That is the unit. That is the unit of potential. Potential, the symbol is V, or even potential difference. It's one and the same thing. Potential difference, which means delta V. Also keep in mind, potential difference, potential energy, etc. all are scalar quantities. They do not have directions. They do not have directions. Also, sign-wise, just like potential energy could be positive or negative, same way this can be positive also or even negative as well. Sign-wise it can be positive or negative also. Is this point clear, everyone? How we define 1 volt? 1 volt is when you do 1 joule of work per coulomb. Okay, when you do 1 joule of work per coulomb, that potential, that energy per unit charge is called as 1 volt. It is a scalar quantity because no direction associated with it. Just like energy, work, power, all these are scalars. They don't have direction associated, nor do they follow the laws. And they can be positive or negative, just like potential energy could be positive and negative. Right, perfect. Now, what you see from here, and this particular example is that, see, when you move from one point to the other, initial to final point, there is some work done externally, which I call it as the change of the potential energy. If that charge which is moved is Q, so if I divide this with Q, what I get is basically potential difference. What I basically get is nothing but potential difference. This is nothing but, again, V final minus V initial. This exact same thing, they could have written it in a very simple way, but they complicated it in these paragraphs. Okay, they have written something and all, but this is the main gist of it. Whatever important lines are there, I have highlighted them for you. Other things will just confuse you guys. So that is why you need to hear my explanations. Okay, so what I just said over here, final minus initial, which is change of the voltage, change of the potential, is work done per charge, which is change of energy per unit charge, which I can also write it as divided by Q, and this is nothing but U final minus U initial divided by Q. If you notice, the same equation is there here also. Where did it go? Final energy minus initial energy by Q. Final potential minus initial potential. This is the explanation of that, a detailed way to write this. I hope this is understood by everyone. I hope this is understood by everyone. Alright. Till this point, everybody clear? Till this point, everybody clear? Very good. Now, by chance, if I make my initial point as infinity, and then come to certain point, then what happens is, just like before, the potential at infinity is assumed as zero. This is called as your zero reference. Remember, what you take as zero does not matter. What matters is the difference. What matters is the change. Remember this? I just gave you that example right over here. What you take as zero reference does not matter as long as the change is the same. Same thing is applicable even for potential. Same thing is also applicable even for potential. That's what they mention. All the remarks made earlier regarding energy also apply for potential. So we should take infinitely small charge like this one. So you should also take infinitely small test charge to obtain the work done. Also, basically we take it from infinity to that particular point. Also, the external force is equal and opposite, blah blah blah. All these things are still valid. So coming back over here, I can just simply say the potential at that particular point minus the potential at infinity is equal to work done externally from infinity to that particular point, the whole thing divided by our test charge. The same thing, work by Q, V final minus V initial, right? This, but V infinity is 0. So just use this fact over here. So I will get that the potential at any particular point is nothing but simply how much work you need to do to bring that charge to that particular point, from infinity. That's very important. And just divide it with the charge. That's the definition of electric potential at a point. This was potential difference. This was potential. This was potential difference. Potential difference can be between any 2 points. Potential is at a point with respect to infinity. Getting it, everyone? Is it absolutely clear? Sir, in Jungle Book there is uploaded motion of 1D nodes, something wrong. Okay, I'll have a look at its theory. I'll just correct it if there is some mistake. Okay, don't worry. Yeah, I hope everybody knows that we are maintaining the Jungle Book. In case you are not aware of it, as you are watching any of these classes, let me tell you. So hopefully it should be there here. Jungle Book. Where is Jungle Book? Yes, sorry, not Jungle Book, Treasure Box. Jungle Book is in the JEE channel, my bad. So you have the Treasure Box where we maintain all our notes. For JEE channel it is called Jungle Book. Okay, it's one and the same thing but for 2 different channels. So you can see all the lectures are maintained over here with the YouTube links, notes whenever we conduct that class. If there is a previous year question test, we keep it, chapter wise PYQ PDFs also, and NCERT solutions if it is there for that particular chapter, right? All those things are maintained in the Treasure Box. So make sure you are checking them out and downloading wherever necessary. All right. So this was potential difference versus potential. Now, in the next thing, they have calculated what is the electric potential at that point by integrating this. So this derivation not needed. Just logically think and tell me, if potential is the work done by Q, and before this I had told you that energy was just the work done without dividing it by Q. And we had found out the formula of energy, which was KQQ by R. Think about it. What will be the value of potential due to a point charge? What will be the value of potential due to a point charge going by this particular formula? It will be just exactly KQ by R. Yep. So the potential at any point will simply be KQ divided by R. K is the Coulomb's constant. Nothing more, nothing less. That's all. So you have a charge over here. You are at certain distance from it. So at that certain distance, at this particular point, there will be some potential. So what is the potential at that point? KQ by R. Because remember that KQQ by R was for energy. So if you divide it by Q, that Q and Q will get cancelled. So that's why you will be getting this. That's why you will be getting this. So look at this definition over here. Potential is work by charge, but work is energy. Energy was KQQ by R. So Q and Q gets cancelled. That's how you basically end up with this particular formula. Yes, Krishna, correcto. Perfect, Paul. Awesome, Madhumati, Pavitra, Mukunda, everyone, Nagaswin. Clear. Shall we go ahead to the next pointer? Now, what they have given over here is basically some graphs, okay, variation of potential with R and the field with R, okay, in the black and the red curves. So, all right, this should be positive, blah, 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 how the electric potential and this varies. Now, this graph is very interesting to see. Look at this. If you look at electric potential has the term 1 by R in it. Makes sense. V is inversely related to R. If you remember electric field at that same point, it was KQ divided by R square. So it is inversely related to square of the radius. Electric field is square related inversely. So that's why electric field will fall more rapidly with distance. You can see that right over here, the electric field will start falling more rapidly. So it is gone below over here as compared to the electric potential. It will fall faster with increase of the distance. That's what it means. That is what this graph is all about. That's the only thing which you should know. Okay, and there is nothing great about this particular paragraph, so don't worry about it. Yeah, okay, I have already mentioned that electric potential can be positive or negative right over here. It is positive or negative depending on the charge. So if you have a charge which is positive everywhere around it, it will have positive potential. If you have an electron like charge, then no matter where you go around it, it will have negative potential. Here it will have positive potential. Okay, that's what it means. Cool. Let's go ahead and see some maybe questions. Calculate the potential due to a charge 9 centimeters away. Obtain the work done in bringing that charge from infinity to that particular point. Does the answer depend on the part taken by this particular charge? Okay, let's do this one by one, my dear students. Calculate the potential due to this particular charge. So electric potential at a point P is given by KQ divided by R. Coulomb's constant is 9 into 10 to the power 9. The electrical charge is 4 into 10 to the power minus 7. And the distance which is there, R, it is 9 centimeters. So 9 into 10 to the power minus 2. This 9 and this 9 will cancel. Okay, this 9 and this 9 will cancel. 4 will remain. This 10 to the power 9 is there. Minus 7 minus 2, this will become minus 5. So hence it will become 4 into 10 to the power 4. This will be volts. This will be basically volts. 4 into 10 to the power 4 volts, which is the correct answer. So this part A is done and dusted. All right, sorted it is. Let's go to the second part. Obtain the work in bringing a charge from infinity to that point. Remember the definition of potential. It was the work done in bringing a charge from infinity to the point upon the charge itself. So the work done to bring a charge from infinity to the point will be the potential multiplied by the charge. Take that charge on the top. So what is the potential? It is 4 into 10 to the power 4. What is the charge? The charge is 2 into 10 to the power minus 9. So 4 2s are 8. 4 2s are 8. 4 and minus 9, guys, that will make it 10 to the power minus 5 joules. So the work done also we have calculated, it is nothing but 8 into 10 to the power minus 5 joules. Last part, does it depend? Does your answer depend on the path? The answer is no, because it is conservative force. Conservative force, the characteristic is the work done does not depend on the path taken. It is path independent. It is path independent because it is a conservative force. Everybody clear with this first question coming up on your screen? The next one now. Hello Naveen Kumar. Good evening. Very good Darshini. Awesome. Very good Krishna. Mukunda. Yes. Awesome. Moving on to the next one. Now that we have learned how much is the potential or potential energy due to charges, the next thing is finding the potential due to a dipole. Just to recollect what a dipole, di is 2, pole is polarity. So two polarities together makes an electrical dipole. As we have learned, an electrical dipole consists of two charges separated by small distance. Total charge is 0. The dipole moment vector is q into 2a, which points in the direction of this. All this was done before, and the field of a dipole at a point P depends not just on the magnitude but also on the angle between them. Further, the field falls off not by 1 by r square but as 1 by r cube. All this particular part was done in the chapter 1. Chapter 1, this is more like a recap. This is more like a recap. So just to recollect what we have done till now, if there is a negative charge and if there is a positive charge of the same amount, negative and a positive charge of a same amount, that is called as a dipole. Two charges separated by a small distance. Remember, we had argued about why that 2a doesn't make sense, but still we use it because it is there in NCERT. And we define a dipole moment always going from the negative charge to the positive charge. Negative charge to the positive charge. This dipole moment magnitude, this magnitude is q into 2a. This is our dipole moment. This is our dipole moment. And this particular dipole creates an electric field around it. We have discussed this. It creates an electric field around it, something like this. We have discussed this. Oops. We have discussed this before. Axial point, equatorial point, etc. So this is how the electric field due to the dipole is, and in general you will see that the field is proportional to 1 by r cube due to a dipole for long distances, for far away distances, when you are really far away from the dipole, right? We have discussed this. It is not 1 by r square. Is that right? Do you remember all of these pointers which we have discussed in chapter 1? Okay, if you have missed that lecture, just make sure you check out the series on our homepage only. So you can see the physics playlist is here, you can see the chemistry playlist is here, the zoology, botany playlists are here, counseling playlists, everything are over here, guys. All the strategies, everything is right over here. So you can just go back to any of our live classes. Okay, you can see we have done this already. Electric charges and fields. This was the part 2 and this is the part 1. We have done this already. Okay, cool. So that was a quick recap. Now comes the next part where we are trying to now find out the potential due to the dipole. We have already found the field due to a dipole. Field due to the dipole is already found in the previous lecture. We are now interested in the potential because we just now discussed potential, right? Okay. So We take the origin as the center of the dipole. We know the electric field obeys the superposition principle since potential is related to the work done. So electric potential also follows. Very interesting, important point. So electric potential, electrostatic potential also follows superposition principle. Thus the potential due to, thus the potential due to the dipole is the sum of the potentials due to the charges q as well as minus q. Makes sense. And that is why you get the total potential as this plus this, where R1 and R2 are the distances from the charges. And then they do this beautiful derivation and get a formula. Let me explain this first, what it means. Just imagine a triangle. Imagine a triangle like so. Imagine there is a charge q. Imagine there is a charge negative 2q. And let's say there is a point which I am considering over here. A point which I am considering over here. The side length is basically a. Question is, we have to find the potential at that particular point. Okay. What do we do in that case? Because I know only the formula for potential due to a single charge, meaning due to this charge I know, due to this charge I know. So due to all the charges, what is the potential? Well, they say even electric potential follows the superposition principle, which means you just add the potentials. But the best part is right over here, which I showed you. Where is it? Scalar. Electric potential is a scalar, which means you don't have to worry about the directions. Signs, yes, but not the directions. So coming back over here, so the total electric potential at that particular point will be potential due to Q plus potential due to negative 2Q. This is using just superposition. Superposition. So potential at point P due to Q charge will be K, Q divided by A. Due to minus 2Q charge will be K, negative 2Q substituted as it is, divided by A. So same things are there, just this is negative 2. 1 minus 2 is minus 1. So it will be minus KQ divided by A. That is the potential at that particular point using superposition. Is that clear, everyone? So now think about it. If you have a negative Q charge and if you have a positive Q charge, and what we do over here is the center of the dipole, we take it as our origin. This is basically A, this is also basically A, and you consider any random point, guys. You consider any random point. Let's say this random point is right over here. Then that point from the positive charge will be at some distance, and the same point from the negative charge will be at some other distance. Don't have to worry about the directions, keep in mind. So from the positive charge and the negative charge, they are taking some distances, which is R1 and R2 are the distances from Q and minus Q. So this is, let's say, R2. Let's say this is basically R1. So think and tell me what will be the potential at that particular point. What will be the potential at that particular point? Obviously, it will be the potential due to the positive charge plus the potential due to the negative charge. What is the potential due to the positive charge? Due to the positive charge, it will be K, Q divided by R1. What will it be due to the negative charge? It will be basically K, negative Q divided by R2. So if you want, you can take few things common. You can take few things common over here. So the potential at that particular point will be KQ common, 1 by R1 minus 1 by R2. Is this clear? That is what they have done over here. And that K also, you can just further write it down as 1 by 4 pi epsilon naught. This you can put Q, and this is 1 by R1 minus 1 by R2. Is that absolutely clear, my dear students? Everyone? Now that particular point may be at some distance over here. That distance they have written it as r, making an angle theta, So after using some approximations, derivations is not important even for NEET, and yeah, so don't have to worry about it. You write R1 in terms of R2, R1 in terms of R, R2 in terms of R using trigonometry and some approximations. And then after solving and approximating, finally you get the potential at that particular point as 1 by 4 pi epsilon naught, or basically let's just put K over here. You also get R over here. You get basically Q over here into 2a, and then you also get cos theta and the whole thing divided by r square. This is exactly what you get. KQ2a cos theta by r square. KQ2a cos theta by r square. Once you get this, we immediately think, wait a minute, I know what this particular term means. This is our dipole moment. Charge into 2a. Hence, I write it as K into dipole moment cos theta, the whole thing divided by r square. That is the potential at, in general, any point around that dipole. Potential at any single point around that dipole. What is theta? The angle which is made by the point with respect to the dipole moment. What is our distance of the point from the dipole? All this is valid assuming R is much larger than our A, basically short dipole. The dipole is very small as compared to the distances which you are at. Only then this is valid, which is always true. Yes, Kp cos theta by r square. Remember, in field, what used to come? In the electric field formula, what used to come? R cube used to come, R cube. So one R has gone off and it has now become R square. Usually for potential due to a point charge, if you remember, R comes below. But always for dipoles, the powers are 1 higher. When usually electric field is 1 by r square, for dipole it becomes 1 by r cube. If electric potential formula is 1 by r, for dipole it becomes 1 by r square. That is what they have eventually got right over here. Binomial theorem, approximations, all this not needed, guys. Don't waste your time over here. Okay, so this is what it is. Now you can take two special points over here. One is basically our axis, one is our equator. If you remember what is axis and equator, I'm pretty sure you will be able to get it very easily. So if this is our dipole, and let's say you are anywhere over here or here. Basically this is the axial point, and when you are on the axis, remember on the dipole axis, theta is either 0 or 180 degrees. So what will happen to this particular formula? Cos 0 is 1, cos 180 is negative 1. So it will become either plus or minus 1. So hence you will see that the the potential will become either plus 1 or negative 1 Kp by r square. So the potential will just become plus or minus Kp divided by r square. Is that okay, everyone? If you are on this side, it will be positive. If you are on this side, it will be negative because you are closer to the negative charge. Do not forget, this is the negative charge and this is our positive charge. So on this side, it will be more positive. This side, it will be more negative. Similarly, if you basically go over here, what is this region called? This is called as our equator. Remember, this was called as our equator. So equatorial plane, yes, at the equatorial plane, theta is 90 degree. The angle which you make will be 90 degree. And what will be the potential? Think about it. What will be the potential? Cos 90 will be a big fat 0. Yes, cos 90 will be a big fat 0, guys. Hence, at all this point, you will have 0 volts. What a beautiful, beautiful thing. On this side it is positive, this side it is negative, exactly on the equator it is 0. So the 0 separates the positive and the negative. 0 separates the positive and the negative. Okay, clear till this point? All these formulas are clear, everyone? How they get? I'm not sure, Harish. We'll see how much we can do today. Whatever is left over, we'll have a part 2. Okay? We are not hurrying into anything. See, because that's not the whole purpose of conducting these classes, right? The purpose of these classes is to make you understand. Now, important features of potential due to a single charge. That is, if you rotate the position vector r about basically the axis, symmetry that you are rotating, keeping theta fixed, the points corresponding to P on the cone so generated will have the same potential as P. Okay, so basically what they mean to say is that you have to visualize this a little bit. Imagine this is our dipole moment. Imagine this is our dipole moment. Also the angle between the position vector and r. Okay, so that means if you rotate the position vector, so this was our position vector r to locate that particular point. This was that particular angle theta. Now imagine you make this dipole as your axis, this dipole moment vector's direction as your axis. You take this point and rotate it in 3 dimensions. Just visualize this, guys. Just you will have to visualize it. Rotate this in 3 dimensions with this as our axis. With this as your axis. You will see at all these points, the potential will be the same. This will behave like a cone now. This will behave like a cone. So at all these particular points, the potential is going to be the same. The potential is going to be the same. The cone so generated will have the same potential as that of the point. The cone is the one which I have generated over here. If you rotate the position vector r about the dipole moment P, keeping theta fixed, all those points will have the same voltage. That is one thing which is very interesting to note about this diagram. The electric dipole potential falls as 1 by r square, not 1 by r, which is again what I told you just some time back. See over here, usual formula of electric potential, kq by r, kq by r, where is it? kq by r, kq by r, everywhere kq by r, usual formula. But the moment you go for an electric dipole, the powers get raised, so it is 1 by r square. That is what has been mentioned right over here. So let me just mark that also. The electric dipole potential falls off at large distances as 1 by r square and not as 1 by r, which is for a single charge, which is the characteristic due to a single charge. For a single charge it is 1 by r, for dipole it is 1 by r square. That is the main significant. Pavneet will have the PYQ series once all the chapters are completed, but also let me remind you one simple thing. As we are doing these things, remember RNA series is continuing. In RNA, we involve PYQs as well as the concepts. Okay, so in the RNA series, NEET PYQs are a part of it. Not all the PYQs, but as many PYQs as possible, along with some conceptual questions as well as Tatva questions. So that is a part of RNA series. NCERT series obviously will be sticking to NCERT, but from the NEET perspective. Why, sir, cone has the same potential, Krishna? Because of symmetry. So think of it like this. Imagine this is our dipole axis. I see that the potential at this point is 5 volts. If I go here also, same voltage, because this diagram I can tilt it back over here. If I go here, voltage will be still 5 volts because I can just tilt this diagram like this and you will see it's the same diagram. So this dipole moment becomes like the axis, and all the points which are at the base of the cone, which are at the base of this particular cone, will have the same volts, 5 volts, 6 volts, 7 volts, whatever it is. Are you able to visualize it now? Okay, because of symmetry. Whether I go like this, 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 same distance, same angle, voltage will be same. Okay, cool, great. Potential due to system of charges, I think this we already did over here. Where is it? I just gave you this example. When multiple charges are there, then you take the potentials due to each charge and you add them. And why does this happen? Because electric potential follows superposition principle. I just mentioned that to you right over here. So the same thing they have repeated. When there are many charges, then you can see electric potential by superposition principle. The potential due to the total charge is the algebraic sum of the voltages of individual charges. So that is why this holds true. Potential due to 1, potential due to 2, potential due to 3. If there are multiple charges, each charge will generate its own individual potential, and you add the potentials, you will get the net potential. You will get the net potential, but you add them without direction. Direction is not important because it's a scalar. Only for electric field, you'll have to worry, oh, it is here, one is here, they might cancel, component, blah, blah, blah. There is no question only of components. Don't take components over here. Okay, that's what they have mentioned over in this particular part. Now, in the next part, what they say is, we have seen that uniformly charged spherical shell, electric potential outside the shell is as if the charge is concentrated at the center. Thus, the potential of the shell is given by this, whereas the total charge on the shell or the radius r, the field inside is 0. This implies potential is constant inside the shell as no work is done, and therefore electric potential equals to the one on the surface. So, whatever is explained over here, I will explain it on the next slide. I'll explain it on the next slide. Okay, don't worry. Right over here. Guys, if you remember last lecture, we have found out using Gauss law, what happens when you are outside versus inside. Oops. So first time, when you are outside, basically r more than the radius of the shell. Remember, this is a shell. Shell means the charges are only on the surface, on the periphery. It's hollow inside. It's like a hollow sphere. Then you will basically go inside. Where basically r is less than r. If you remember the quantity of electric field, what was it? When you are outside, the electric field was just given by k q divided by r square. Basically, it behaved like a point charge at the center of the shell. Just imagine there was just one single charge at this distance. What is the electric field? Kq by r square. That means the electric potential at that point should also be like the potential of a point charge, which means it should be kq divided by r. Did you understand why this comes? Because it behaves like a point charge. So just think as if you have basically a point charge, and then you are at certain distance r from it. So definitely there will be some electric field, and at that particular point you will have some potential. It will behave like a point charge at the center. Is that absolutely clear? Everybody with me? Awesome. But when you are inside, there is one interesting thing which happens. We saw that in the previous lecture, that the electric field just becomes zero. Now, the moment electric field becomes zero, one usually might think, sir, if there is no net electric field here, wouldn't the potential also be zero? I would say, don't think like that. I would say, don't think like that. See, if field is zero, won't the electric force also be zero? That means, won't the work done to move the charge, work done to move our test charge be also zero, because no force is there? No force, you don't have to do any work. That's it, it will move on. If you just push it, it will keep moving. That's it. No work has to be done. So if no work has to be done to move a charge, that means there is going to be no change in potential energy. That means there will be no change in potential. No change in potential. That means that the potential is same. That means the potential is just going to be the same everywhere inside. It is going to be same everywhere inside. Do you guys agree with it? So just imagine this is the surface. This was basically outside. This is basically inside. Whether you are here, potential is the same. And we know that if you are just on the surface, we can see that the potential just on the surface using this formula will be kq divided by r. So whatever potential is here, it just continues. It just continues everywhere. It will be the same here, everywhere. In fact, everywhere on the surface also, the potential will be the same. That means if it is the same, how much should it be? It will still be kq divided by r. This is the radius of the shell. Be very, very careful. This is not small r, it is capital R. So it is not dependent on where you are. It is the same. It is basically constant inside. That is what they have done over here. That is the explanation of this particular paragraph. Is this logic explanation clear, everyone? Yep. Okay. Sukanya, definitely, my dear warriors. Let me complete the RNA series very soon, and we will have the PYQ series also. But also let me tell you one interesting thing. If you want all the PYQs, all chapters, all PYQs, I have done it for you. Do you know that? Yes. I don't know whether you know this. On this channel itself, just search for PYQs, physics. I hope it will be shown. Yes. There were 1,000+ questions, guys, which we did. Yep, all the 1,000 PYQs. 2019, 2020, 2021, 2022, 2023. Obviously, this year we'll take it probably by the year end. Okay, and we'll incorporate all the other PYQs also. Like there were many sets, right? There was not one set, multiple sets came. So, and a retest also happened. So we'll have a separate set of videos for that as well. But let me remind you, I have taken all the PYQs from 2019 to 2023, and the previous PYQs and 2024, I'll be doing it once RNA series is over. Okay, so have a look at it. It's not just for physics, but you can also do one thing. You can search for chemistry as well. Yes, it should come up. Yes, see, Diksha ma'am is there. 1,000 PYQs. All the things. These are big classes. All the PYQs. I think inorganic was done separately. And I think physical and organic was done separately. So all these lectures are there for all of you guys. Yep. All right, Chitra. Great. Thank you so much. All the efforts only for you guys. Thank you, Warrior Pandus. Thank you. Thank you so much. Okay, moving on. Two charges, this and this, 15 apart, at one point on the line, is the potential 0, take the potential at infinity to be 0, which is pretty much standard. So let me show where the charges are. Two charges are separated by 15 centimeters apart. So one charge is positive 3 into 10 to the power minus 8 coulomb, and let's go 15 centimeters from it, and I'll reach here. And how much is the other charge? Negative 2 into 10 to the power minus 8 coulomb. So the question is, at what point on the line joining them do you think the potential is 0? All right. Now, in order to solve this particular question, what will you do? You will choose some point where the potential is 0. I can choose that point to be anywhere. Maybe it is here, maybe it is here, maybe it is here. Okay, where do you think most likely it will be? Where do you think most likely it will be? I think it will be somewhere in between. I don't know where that point is. Maybe I'll choose that particular point to be here. And at what point? Let's say from this side it is x centimeters. So from this side it will be 15 minus x centimeters. From this side 15 minus x, from this side it will be x centimeters. Also, the potential at this particular point will be potential due to the first charge plus due to the second charge using superpositioning theorem. Using superposition principle, we get that. So what is the potential due to this charge at this point? Well, it is K into Q. Q is basically 3 into 10 to the power minus 8 divided by R, which is basically X, plus what is the potential due to that charge? K into minus 2 into 10 to the power minus 8, whole thing divided by basically 15 minus X. But what is mentioned clearly in the question? That the electric potential is 0. That means this point has 0 volts. That means this point has 0 volts. Obviously, few things will get cancelled off, like 10 to the power minus 8, 10 to the power minus 8, K will get cancelled. Bring this guy on the other side. Bring this term on this side. It will become like this. 2 divided by 15 minus x is 3 divided by x. Cross multiply. So 2x is 15 3 is of 45 minus 3x. Take 3x over here. So it will become 5x is 45. Therefore, x will be, I did one silly mistake. I had to multiply it by 10 to the power minus 2. 10 to the power, because this was centimeters, into 10 to the power minus 2. But the best part is this silly mistake won't cost me anything, because anyways it will get cancelled, because it's 0, right? So it will just get cancelled. So don't have to worry about it. Okay, so this will be basically 9 centimeters, because everything I assumed it in centimeters. So that should be the answer. So 9 centimeters from one side. That means from the other side it will be 6 centimeters. I hope this is clear. Okay. Is that understood? So 9 centimeters from here, 6 centimeters from there. Very good. Excellent. Excellent. Awesome. And as you're watching this video, keep smashing the like button in case you have forgotten. Okay. Just a quick reminder, guys, for all the efforts that we keep on doing for all of you. Cool. Moving on. Now, next question over here. Okay. They have given a diagram of electric field of positive and negative charge separately. For positive, for negative, some points are marked P, Q, A, B. Give the signs of potential differences. Give the sign of potential energy difference for small negative charge between the points Q and P, A and B. Give the sign of the work done by the field in moving a small positive charge from Q to P. Give the sign of work done by external agency in moving the negative charge from B to A. Does the kinetic energy of the small negative charge increase or decrease from B to A? All sorts of possibilities. All sorts of possibilities are given over here. Okay, let's do this, guys. Everyone, let's do this. Okay, take your moment. Try to solve this. Let me just drink some water. Let's do. Okay. First, give the sign of potential difference between P and Q. I'll tell you what, best thing to do in such problems is to put some random values just for the sake of it and then solve the problem, because this is positive charge. So it will have positive potentials. As you go far away, the potential will decrease. So I'm just taking an example. Okay. So let's say it is 20 volts at point P. Let's say at point P, it is basically 20 volts. At point Q, let's say it is 15 volts. Example. Similarly, over here, because this is negative, this will become more negative when you become closer. Let's say it is minus 30 volts. Here it will become less negative. Let's say it is become minus 20 volts. Chumma, I have taken some examples for our understanding. Give the sign of potential difference Vp minus Vq. Come on, my dear warriors. Let me just create a duplicate of this. So if I do Vp minus Vq, what will happen? Vp minus Vq, it will be 20 minus 15, which is basically plus 5. So this will be positive, guys. What about Vb minus Va? What about Vb minus Va? Take examples, it becomes simple. Minus 20 minus 30. So 30 minus 20, it is becoming 10. Is it right? So it is also going to be positive. Is that right, everyone? Both are positive. Everybody got it? How simple it is when you take examples. Yep. Next, this part is done. Give the sign of potential energy difference of small negative charge between the points Q and P and A and B. Give the sign of the potential energy difference. Okay. See guys, if you remember the formula, it will be easy. Delta V is delta U by Q. That means delta U is delta V into the charge. Now, in both the situations, whether it was Vp minus Vq or Vb minus Va, so potential difference between Ba or potential difference between PQ, both these terms were positive. We just saw that. The first answer, they both are basically positive. What charge have you taken? Look at it, given negative charge. So if you multiply it with negative charge, what will happen to the value of the change of energy? Won't this be also negative, guys? So won't the sign of the potential energy difference be negative and negative for the second answer? Just check this out, everyone. Yep. Everyone with me? Yes. Okay. Clearly, it will be negative if you go between VB and A and P and Q. But here, what they have asked is not between P and Q, they have asked between Q and P. And instead of B and A, they have asked between A and B. So, I think if you reverse this, the answer will also get reversed. So, this will become positive and this will become positive. So, remember this is BA. So, same thing I can say. If I do delta V AB and if I do basically delta V QP, both these answers will be definitely negative. And if you multiply it with a negative charge, negative into negative is positive. Is basically positive. Hence, the answers for both these things will be positive only because of the order of the events. They have asked between Q and P, not P and Q. This is between P and Q. This was between Q and P. So I have to reverse the sign. That's the only difference. So small things which you need to keep in mind. Is that okay? Shall we move ahead to the next one? Okay. Give the sign of the work done by the field in moving a small positive charge from Q to P. Okay. So for the next part, what I will do is, when you want to do work and you are moving a charge from one point to the other, we know that the voltage difference is the work done per unit charge. That means the work done is the voltage difference multiplied by the charge. The work done by the field now that I have asked. Okay. Now this work done is always external work done. This is external work done. We know external work is negative of the work done by the electric field. So work done by electric field will be exactly negative delta V into Q. This was external, this is electric, that's why the minus sign has come. So you have to play with the signs, guys, that's all. You have to be very careful with the signs. Now once I have obtained this particular relationship, I think it will be easy for me to solve question number C. I have to move a positive charge. So if you talk about positive charge, so positive charge is there, and I have to move it from Q to P. So voltage difference between Q and P, work done to move it from Q to P. What is delta VQP? What is delta VQP? We have figured it out over here. QP is basically a negative quantity. That means negative into positive will be negative quantity. Negative into positive will be basically negative quantity. Hence, the answer for this will be negative. Is that absolutely clear how we are doing it? Very systematically. Don't get confused because I don't know what the solutions are, but it's little complex to understand this. So our answers are correct. First answers were positive. Yes. Second answer is positive. Yes. And this is negative. Yes. Perfect. We are on the right track. Let's go to the next one. Give the sign of the work done by external agency in moving a small negative charge from B to A. Same concept. Same concept. The work done to move from B to A, just like P to Q or Q to P, it will be nothing but delta VBA multiplied by the charge. What is the charge? What is the charge? In moving a small negative charge, this is negative. What is delta VBA? Delta VBA. Delta VBA is positive. This is basically positive. Hence, this will be negative, guys. Hence, this will be basically negative answer. Is that absolutely clear? See if you guys are understanding this concept. Everyone with me? Oh, but this was, be careful. Oh, sorry. This was one small mistake. I took, this is work done by electric field. Sorry, this is work done by electric field. The question is, what is the work done by external agent? So sorry, guys. So if this is work done by electric field, so work done by external field, external force in moving it from B to A, that would be negative of that. So it will be positive. So I think this answer will be positive. This answer will be positive. This was external. In the previous question, it was by the field. It was by the field. I hope this is clear. Okay. If it was asked by the field, the answer will be negative. If it is asked by the external, it will be positive. Last question, does the kinetic energy of a small negative charge increase or decrease in going from B to A? Now, in going from B to A, let's see what happens. B to A, delta VBA was positive. Delta VBA is basically positive. And going from B to A, sorry guys, if I'm going from point number B to point number A, what I will actually do, if I'm going, this is initial, this is final, this is initial, this is final. So I will be subtracting VA minus VB, final minus initial always, final minus initial always. This is nothing but VAB, and VAB is basically negative. VAB is basically negative. Okay, I'll keep that in mind. And I am taking a negative charge. So what happens to the kinetic energy, they have asked. Okay, one thing I know that delta U is delta V into the charge. So delta U, in taking it from this, is delta V AB multiplied by the charge. Remember, our charge is clearly mentioned to be negative. This also is negative. Negative multiplied by negative will make it positive, which means our potential energy has increased. This means potential energy has increased. But remember, mechanical energy has to be conserved, which means kinetic energy will have to decrease. This is only because it has to be conserved. Hence, the answer will be decrease. Yes, the kinetic energy is decreasing, and previous answer was positive. Yes, that is also correct. That's how you solve this question. Isn't this one of the best conceptual questions? Everyone? Isn't this one of the best conceptual questions, everyone? In NCERT, this chapter? Yeah? Because it's so confusing because of the science and everything. And it's all got to do with these few slides over here. The few slides over here, where is it? This one. All these slides over here. This. And even this one over here. The science. It's all about the science. It's all about those science. Okay. So if you know those signs and the formulas, it will become very, very straightforward. Moving ahead now. So this is done. So now let's go to equipotential surfaces and the relationship between the potentials and the fields and potential energy of a system of charges and all these concepts, and potential energy in external field of a dipole. All these things we have to complete as much as possible today. I'm not sure whether we'll be able to complete the chapter today, but we'll try to do as much as possible. Okay, let's do guys. The next concept. Equipotential surfaces, 2.6. Full of josh, full of energy, everyone? Yep. Okay, let's do. Equipotential surfaces is a surface with constant value of potential, as simple as that. Is nothing but an equipotential surface is a surface with constant value of potential at all the points on the surface. For a single charge, the potential is given by this, shows that the potential is constant if R is constant. So basically, in this particular example, the equipotential surfaces of a single point charge are concentric spherical surfaces centered at the charge. Now that the electric field lines for a charge are radial lines starting from ending of the charge depending on whether Q is positive or negative, clearly the field at every point is normal. Okay, very important. The electric field at every point is normal to the equipotential surface passing through that particular point. This is true in general for any point. In fact, it is always going to be true. So for any charge configuration, the equipotential surfaces through a point is normal. Normal means perpendicular to the electric field at that particular point. And the proof of that is very simple. They have given this particular thing. If the fields were not normal, the equipotential surface would have non-zero component. To move a unit test charge against the direction of the component, the work would have to be done, but this is contradicting the definition. Hence, there is no potential difference between the 2 points on the surface, hence no work is done. Hence, there must be normal equipotential surface or offer an alternative visual picture in addition to the picture of the electric field lines configuration. Okay, so let's understand this. Imagine there is some charge here, some charge there, some charge here, etc. Let's say I notice the potential over here is plus 12 volts. I notice another point which has the same voltage, which is plus 12 volts. I notice another point which has the same voltage, plus 12 volts. Another point which has plus 12 volts. Another point which has plus 12 volts. And I see there are many more such points, and I keep joining those points together. and maybe it becomes like a curved shape. That collection of all those points is basically called as an equipotential surface or a line. It will be a line if it is in 2D. If it is a 3D, then it will become a surface. Now you can have more such electric potential lines, equipotential lines. Maybe you might have another set of lines which is like this. Maybe it's of 11 volts. Maybe it is of 11 volts. Maybe you might have another set of lines maybe like this over here. Maybe it is 10 volts. Maybe again it will go here and there, maybe on this side too, and maybe it is plus 13 volts. So this is a set of equipotential lines. This is a set of equipotential lines or surfaces. If you go anywhere on this line, the potential is same. If you jump from one line to the other, you will get a potential difference. You will basically get a potential difference. So imagine if you have one equipotential line given like this, and if you have another equipotential line given like this, these are two different equipotential lines, and if somebody makes a jump from here to here, this is initial, this is final, obviously there will be potential difference because you are going from one point to the another, and that will be final minus initial potential. So V2 minus V1, V2 minus V1, that will be the potential difference between equipotential lines, potential difference between equipotential lines. Is this point absolutely clear? Yep, very good. Now, what they say is also that if you take a simple point charge, somewhat like this, the equipotential lines are nothing but concentric circles, which kind of makes sense also, because obviously at the same distance the potential will be the same. So if you draw concentric circles like this, you will see that the potentials at all these points on those circles will be the same. So these are equipotential lines. All the points have the same potential. All these points have new same potential. These have a new same potential. I can call this V1, V2, V3, so on and so forth. Now, if you superimpose on it the electrical field lines, they will look somewhat like this. Right? Like this. And show even more. Like this. These are your electrical field lines. Notice how the electric field line is everywhere perpendicular to the equipotential lines. It is not just for a point charge, but it is also true for any other random body also, like this one. You will see that at every given point, electric field line will be perpendicular. If you show some electric field line, it will definitely be perpendicular to the equipotential lines. So this is a general phenomenon, not just associated with point charge, but every charge configuration. Now, why does this happen? Is because they have explained this in this particular paragraph by a method called as contradiction. I will explain to you in a very simple way. Guys. See, imagine this is one equipotential line. Let's assume that the electric field is not perpendicular but making an angle. Okay, the electric field is making some kind of an angle with the equipotential line. If it is making some angle, then there will be two components of the electric field. One component which is basically perpendicular, and there will be other component which is basically parallel to the equipotential line. One which is perpendicular to the equipotential, one which is basically parallel. Everybody agrees with this? One which is perpendicular, one which is parallel to the equipotential line. The problem is with this parallel component. If there is electric field parallel to the equipotential lines, that means along the equipotential line, what will happen? There will be a force, electric force in that particular direction. If there is electric force, what does it mean? There will be a work which will be done by the electric field, okay, in that particular parallel direction, in that basically parallel direction along that equipotential line. If there is work done, that means there will be change of electrical potential energy. If there is change of electrical potential energy, that means there will be potential difference, electrical potential difference along that equipotential line, which itself contradicts the definition of equipotential line. If you assume the field is making some angle, there is a component of the field, that means there is a force. If there is a force, there will be work. If there is work, there is change in the potential energy. That means there is change in potential. But how can you change the potential on an equipotential line? So this is the contradiction part. So that means it contradicts basically the definition of equipotential line. That means our assumption is wrong. That means our assumption that the electric field is making an angle, electric field is making an angle is basically wrong. Hence it can't make any angle. Hence definitely the the E parallel component must be 0. So only this can exist. Only this can exist. Electric field lines are always going to be perpendicular. Is that okay? That is the proof for it. Interesting? Amazing? That is what has been explained here in a very different way. But yeah, I hope I made it very straightforward and logical for all of you. Moving on, for a uniform field, say along the x-axis, the equipotential surfaces are planes parallel to the yz plane as shown in 2.10, which is this diagram, I believe. I think the diagram went on different page. Okay. Equipotential surfaces for a dipole and two identical positive charges are also shown in these diagrams. Okay. See guys, if electric field is uniform, look at this. If electric field is basically uniform, that means the field lines will be parallel. That means the field lines are parallel to each other. Do you see that? The electric field lines are parallel. And what about the equipotential lines? They should be perpendicular. That's why you see that the equipotential surfaces which are shown over here, they are basically planes which are not just perpendicular but also parallel to each other, one after the other. Each plane will be potential V1, V2, V3 like that. Are you able to visualize it? Are you able to visualize it, everyone? So think of it like this. If this was my electrical field line, this page will be a equipotential surface because it is perpendicular. After some more time, you will have another equipotential surface. After some more time, equipotential surface. So they are basically parallel planes one after the other. Cool. That is the first example. Then they give about a dipole. This is a dipole. You can see that. So how they are concentric circles, and slowly you will see this will basically become like this, like this, like this, like this, and eventually you will get one very interesting line in between over here. This line over here, this is basically 0 volt line, 0 volts. On a equator of the dipole, the potential is 0. Remember that? And on the positive side, it is positive voltage. On the negative side, it is negative voltage. We have seen this for a dipole. Where is it? We have seen this for an electrical dipole. I just showed it to you. On the equator, it is 0 volts. On this side, it is positive. On this side, it is negative. So if you show those potential lines, how they look is exactly like this. For two positive charges, it looks something like this. They keep on becoming bigger, and after a point they merge together, they become like this. And if you go really far away, then it becomes like this, and very, very far away, it almost becomes circle, because when you go really far away, think about it, those charges come so close to each other, they virtually become one single point charge, so they start becoming circular. So the shape loses its characteristics, so you will probably see it going like this, and then finally almost nearing a circle. Almost nearing a circle. Is that understood? That's what happens for positive charges. Same thing will also be true for negative charges as well. Okay, that's what they have mentioned. Okay, so now that this is done, equipotential surfaces is understood, give me a thumbs up. Let's go ahead then. Let's go ahead. Awesome, awesome. Let's go. Now, the next concept is relation between electric field and electric potential. Very, very interesting thing, guys. Electric field and electric potential, they have done some derivation. I'll explain this to you. We thus arrive at two important conclusions concerning the relation between the field and the electric potential. So guys, let me explain this to you in a very simple way. See guys, if you go from one point to another, whatever work is done by the electric field is exactly the negative work done by the external force, is also whatever work done by the external force is the change in the potential energy. So this minus sign will just follow over here. This is not just true for electricity, but it is also true for spring, gravity, etc. This is in general, always holds true. Now what I do is, I'll just look at this and look at this. Work done, this is from one point to another point, which are separated by a good amount of distance. Imagine the distance separated is very, very small. So I just move a very, very small displacement from here to here. The work done by the electric field will be dW, and this change will be du. This change will be nothing but du. Everybody agrees with this? Everybody? Okay. Now what I do in the next step is the work done by the electric, work done by the electric field dW, I'll write it as the electric force, okay, electric force into that small displacement. I will call it ds or dx or whatever you want to call it. This is a small displacement. This is nothing but du. What is the electric force? What is the electric force? It is nothing but the charge multiplied by the electric field into ds is equal to minus du. Bring this charge over here, so it will become E multiplied by ds is nothing but minus du by q. What is energy change per unit charge? I have given this to you some time back. Come on, my dear warriors. What is energy change per unit charge? If you guys have forgotten, let me show it to you. See, at the start, everything looks confusing, but with time, you will understand it. Change in voltage is delta U by Q. Energy change by charge is the voltage difference. So that means, what should this be? Wow, we have done a lot. So that means this should be nothing but dV. Perfect. So now move ds below over here. So electric field is minus dV by ds. This is the important relationship. Electric field is negative rate of change of voltage with respect to distance. So electric field is equal to negative times, I can say negative times what? The rate of change of voltage with distance. The rate of change of potential with respect to your position or distance. That is the important takeaway. Very, very important. From this, we arrive at two important conclusions regarding the field and potential. Electric field is in the direction in which potential decreases. Its magnitude is given by the change of the magnitude of potential per unit displacement. What it means is that, why that negative sign came and what it means. See, imagine there is an equipotential line here. I call it V1. And let's say it is, example, 10 volts. And let's say I have another equipotential line over here. And let's say the value, example, is 12 volts. I know 100% electric field will be perpendicular to both of them. But will it be this way or will it be this way? This is understood by the negative sign. This negative sign says wherever the potential decreases, that's where the electric field is. That makes sense. If I have this bottle does not want to stay on the top. If I leave it, it falls down. It wants to decrease its energy. It wants to decrease its potential. Same way, even a charge never wants to have very high potential. Having very high potential makes it sad. So it wants to reduce its potential. So the field always pushes the charges in a region of lower energy. That is why you will notice that the electric field goes from high voltage to low voltage. Electric field will basically go from high voltage to the low voltage. So that is what is mentioned. Electric field is in the direction in which the potential energy decreases. The steepest. You cannot say it will go like this because this is the longer path. This is the shortest path by which you can decrease it. So this is the very quick way of decreasing it. It is very steeply decreasing. That's why it's like that. Anyways, it is perpendicular. Its magnitude is given by how quickly the potential reduces per unit displacement at that particular point. What it means is that, imagine this, there is an equipotential line, let's say over here, then you have an equipotential line right over here, and let's say another equipotential line right over here. And the same thing I will do over here as well, like this, and like this, and maybe like this. The difference is the gaps, but otherwise, example, this is 10 volts, or let's make this 25 volts. This is also 25 volts. This is 20 volts. This is also 20 volts. And let's say this is 15 volts. This is also 15 volts. 100% here and here, field lines will go from high to low. So I know the electric field line will be 100% like this. Here also I know it will be like this. But you know what the difference is? Here the potentials are changing rapidly. Here the potentials are changing aram se, coolly, very slowly. This derivative exactly tells me that the rate of change of the potential with position, how quickly it is changing. The magnitude of the field is dependent on how quickly it changes. Here it is changing quickly. That means the field will be strong. That means there will be more electric field lines right over here. It is going to be a strong field. It is going to be a strong field over here. Here, the number of field lines will be quite less. It's going to be a weak field. It's going to be a weak field. That is what the second point explains. So, the magnitude of whom, guys? The magnitude of whom? The magnitude, its magnitude. Whose magnitude? It's mean the electric field's magnitude. The field's magnitude is given by the change in the magnitude of the potential per unit displacement along the perpendicular direction. So how quickly is your potential changing with the distance? Is it clear? Everyone understood this point? Everybody understood this particular point? Very good. Awesomeness, awesomeness, awesomeness. Now let's go to potential energy for a system of charges. They have given one very big paragraph. Okay, I will summarize this for you. Semiconductor will come after a long time, Mr. Cool 501. Yep. So potential energy due to multiple charges. So I'll tell you, they have given all these things over here. Wow. Main thing is, see, if you have been given two charges, let's say Q1 and Q2, there is some separation between them. I call it R12. Do you remember? I have given you the potential energy formula long time back over here. Where is it? Yeah. Between two charges, KQQ by R. KQQ by R. So let's go back over here. So the potential energy between these two will be, between 1 and 2 will be K Q1 Q2 divided by R12. Is that right, everyone? Now just imagine I bring in one more charge somewhere over here. Let's say Q3. This is having some distance R13. This is having some distance R23. So these two will have a potential energy U13, which is K Q1 Q3 divided by R13. The potential energy between these two, which is U23, will be K Q2 Q3 divided by R23. This is a system of three charges. Just imagine I bring in more such charges. Let's say Q4. Now Q4 will have an energy with Q1, Q3 and Q2. So more terms will come. Do you guys understand that? If there are more charges, Q4, Q5, Q6, Q7, Q8, like that till Qn, you will get more such terms. When you add all of them, what you get is the potential energy of the system of charges, which is summation K Qi Qj divided by Rij. What is this Ij? 1, 2, 3, 4, 5, 6, 3, 5, 2, 3, 3, 4, 5 through like that. All these possibilities. So you take all the possibilities and you get the total potential energy of the system. Is that right? So hence the total potential energy of the system is the sum of the potential energies of all the charge pairs. All the charge pairs which are possible. So each pair is Ij. I can change 1, 2, 3, 4. J also can change 1, 2, 3, 4. Getting my point, everyone, till this? Is it clear? That is what they have basically explained over here. And this potential energy does not depend on how you bring the charge. Somebody might bring this charge Q4 by doing this is and here. Somebody might bring it like this. Doesn't matter. As long as their placement is the same, configuration is the same, potential energy will be the same. If you disturb any one of these charges, what will happen? One of these terms will change, the potential energy will change. So disturbing the configuration disturbs the system, changes the energy. So there will be a difference in the potential energy. That is what they have mentioned over here. The path independent, the final expression is independent of the manner. Yeah. So because of the conservative nature of electrostatic forces, we can say that the final expression for U, which is the potential energy for the system, is basically independent of the manner in which the configuration is assembled. In fact, the potential energy is just dependent on the state. State means what is the final manner, final position, final locations, the current situation of the configuration. It just depends on the situation of the configuration and not on the way the state is achieved, and not on how you achieve the particular state. That's what this mentions. As an example, they have given 4 charges at the 4 vertices of a square. I think there is also an additional charge which is at the center, maybe. Okay, 4 charges are arranged at the corners of a square of side D as shown. Find the work required to put together this arrangement. Now if you bring a charge Q0 at the center of the square, the 4 charges being held fixed, how much extra work is needed to do this? Okay, let's do this particular question. What is the side length? It is basically, I think, D of a square of side D. Yes, this is basically D. And what are the charges? Positive, positive, negative, negative. Okay, so positive, positive, negative, negative. All right, let me create a duplicate. Perfect. Now, in order to find the total potential energy of the system, what will we do, guys? Total potential energy of the system, take all the possible pairs. Do not miss anything. Do not miss any single thing. I think we'll also need this distance when we solve the problem. So I will just put this diagonals also for you, just for your reference. How much will be the length of these diagonals? Can you quickly think and tell me? Sides are D and D. Hypotenuse will be, I think, D root 2. Each diagonal will be D root 2. Agree or disagree? Use Pythagoras. D square plus D square is 2D square. Under the root will become D root 2. Yes. So what next? What next? Let's find out the potential energy. This guy with this guy. See, K, Q minus Q divided by D plus this guy with this guy. Let's cover all the sides first. So K, Q with minus Q divided by D plus this guy with this guy, K, Q minus Q divided by D, and this guy with this guy. So K, Q minus Q divided by D plus this with this, K, Q, Q divided by D root 2 plus this with this, K minus Q divided by D root 2. See what is happening. K Q square by D is common everywhere. K Q square by D is common everywhere. This is negative 1, negative 1, negative 1, negative 1. Minus 1, minus 1, minus 1, minus 1. Here 1 by root 2, 1 by root 2. 1 by root 2, negative, negative is positive. So 1 by root 2 is there. Do you see that? So what do I get? K Q square by D, you will have minus 4 plus 2 by root 2, which is going to be root 2. Hence it will become K Q square by D, and you will have root 2 minus 4, which means the total potential energy of the system comes out as a negative value. Is coming out as a negative value. So that is the first answer, I believe. Yes, that is the first answer. So that is exactly what we have got. K is substituted as 1 by 4 pi epsilon naught. Perfect. Now coming to the next part. The first part is done. The first part was done. Let's go to the next part. What does the next part say? A charge is brought at the center. How much extra work do you need to do? See, already the system is configured. You don't have to break your head now. Right now, this particular system has some energy. Okay. Let me write it over here. Compare it with this one. This is your final. This is your initial. You have gone from this to this. In this process, how much extra work needs to be done? The 4 corners are held fixed, so don't worry about them. Don't worry about this, and this. Just assume the base potential energy as something, U naught, X naught, 5 joules, 100 joules, 0 joules, whatever you want. The extra work needs to be done only because of this charge will gain new potential energies. That will gain new potential energies with who and all? With this, with this, with this, and with this. It is now going to get extra potential energies. So guys, that extra work which needs to be done is because of the extra potential energy which that Q naught will have with all other charges. With all other charges. Do you guys agree with this statement? That extra work comes because this Q naught will gain some extra energy with every one of them. All the others already had some base energy. Make sense? Yes, middle NCERT examples are very important. You will see many examples where they have just given the same questions and sometimes even modified questions, in text questions directly in NEET. So many examples, so many cases you will see, not just in bio but also in physics. Okay, so how much energy extra will be needed by that Q naught charge? This will be basically, assume this distance is x, this is x, this is x, this is x. It will be k Q naught into that positive charge which is Q divided by x plus Q divided by x plus this with this. It will be k Q naught with negative charge divided by x plus this with this, k Q naught into Q divided by x plus this charge with this one, k Q naught into negative charge divided by x. Guys, all these terms will cancel and you will get a big fat 0, which means what? You won't need any work to do this. Whatever kinetic energy was there before will remain, whatever potential energy was there will remain. No extra work is needed. So that should be the answer, guys. Yes, so no work is required to bring any charge to that particular point. Yes, that solves the problem. Beautiful question. You have to understand that the charges were already assembled. So it is the extra work, so extra energy. So that means only that charge with other charges. Don't have to worry about other things. Okay. So let's go to the next few concepts of dipoles and everything, guys. And these are conductor properties and dipoles, everything. I don't think we'll be able to complete all the pages today. We'll do one thing. Yeah, I think it's a good time we stop this particular thing, potential energy of a single charge. Maybe only this point we can do. This point we can do. This last example, and then we'll give it a stop. Okay, let's have a look at this. This is the last point which we'll be doing today, and we'll conduct the remaining part in part number 2. Okay, is that right, everyone? Okay, great. Potential energy in an external field, potential energy of a single charge. The source of the field was specified, blah blah blah. We asked relations, but distinct question: what is the potential energy of a charge Q in the field? You know, I sometimes feel that a person who wrote NCERT, you know, Chumma is like one person who wants to pretend as if he is one serious student. Have you met such students? Aram se they will be chilling out in the class. I have met many students because I have already taught in offline, and nothing, they will be looking or dreaming about something, but when the teacher looks at them, or just to show that they are good, they'll be like, sir, I have one very important doubt, because this is happening, and you know, we have a very distinct question because of this, will this happen? So I feel this language is very similar. This question was in fact the starting point that led us to the notion of electrostatic potential, because all other times they were hitting around the bush. Suddenly they feel that something is important, okay, but here we address the question again to clarify what, why again, why did you not ask it over there? Anyways, in what way is this different from the discussion in section 2.7? See, how is this different from this section 2.7? Oh my god, this is crazy, guys. Alright, so the main difference is that we are now concerned with the potential energy of a charge in an external field. The external field is not produced by the given charge, whose potential energy we wish to calculate is produced by some external source, and the external source may be known, but often they are unknown or unspecified. What is specified is the electric field or the electrostatic potential due to the external sources, we assume that the charge does not significantly affect the sources producing the field. This is true if Q is small or the external sources are held fixed by other unspecified forces. Even if Q is finite, its influence on the external sources may still be ignored in the situation where the strong sources far away in infinity are produced finite field in the region. Note again that we are interested in determining the potential energy of a given charge and later system of charges in external field. We are not interested in the potential energy of the sources producing the external field. The external field and the corresponding potential may vary from point to point by definition. Okay. Thus, the work done bringing the charge from infinity to the point P is QB. This work is in the form of potential energy of Q. If the point P has position vector R, this is this. Thus, if an electron with charge blah 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 is accelerated blah blah blah, and they have given about this. Okay. And then they have talked about two charge system and how you basically calculate the potential of two charge system. Okay. Now I'll explain this to you, what it basically means. Guys, see, first of all, it is pretty much, like hitting around the bush here and there. See, whenever you have a charge, this charge will create its field. This field will never create a force on that particular charge. Do you guys agree with this? This field will never apply a force on the charge which created the field. Makes sense, right? Like if it's like I make some students study, that same students will not blame the teacher. The same students will not say, hey, you, what did you do? No. Same way, this field was created by this charge. This field has no right to question this charge. It is just created from it. But this field can affect some other charge and it will apply a force on it, which is basically Q into this particular field. Cool. Now, same way I can also note and say a charge Q might create potentials around it, V1, V2, V3, etc. So let's say some equipotential line is there, V, and when I place a charge Q over here in this particular potential, then what happens is that, remember, this potential is due to Q. This charge is also creating its own potential. Don't worry about that. Because of this charge being placed here, there is an extra energy which is associated. That energy which is associated now between these two charges will be potential due to this Q charge into this particular charge. That's what this is. So the energy of these two charges, will be potential due to this charge into this Q. Right? I hope this is absolutely clear. Potential due to the Q charge into this charge. Alternatively, you can also think this is the same as, imagine this Q charge was here and that was creating its own potential. Let's say the potential at some point is VQ, and then you place this charge Q over here, then you place this charge Q over here. So then the energy of that particular system, will be potential at that point due to this small charge multiplied by the charge. These both are one and the same thing. It depends on whose potential are you seeing and who are you placing. That's all. Does that make sense, everyone? Till this point, is it absolutely clear? Is it absolutely clear, everyone? Also, they mentioned that usually the charge that you place is very small, because if it is not small, then what will happen? If it is big, it will start pushing this or pulling this. Entire thing will change. The potentials will start getting affected because the charge will be in motion. So, we generally take the charge as small. Even if it is not small, it is still okay, because we are trying to find what is the potential energy at that moment. Maybe because this charge is present, If it is big, it will start pushing it. So this will start going away. This will start changing. So energy will change. That's okay. That is understood that we are interested in at that moment. So that is the main gist of this entire paragraph. They have just confused you here and there. They confuse you here and there. Is that okay? So don't have to remember any other peculiar formulas. Just stick with the basics. You will be done with it. So determine the electric potential energy of a system of two charges, 7 and -2, with no extra. Okay. One more thing is there. One more thing is there. Imagine there is another electric field, some external electric field. This is external field. This external field will obviously create some external equipotential surfaces like this. So this is due to some external sources. And in this, I place a charge Q, maybe somewhere over here. In this, I place a charge Q somewhere over here. Let's say this point's voltage is V1, this point's voltage is V2, and then I place another charge maybe over here, Q. Then what will happen is this whole system, the whole system will have a total energy of, this whole system, the whole system will have a total energy of the following things. Observe carefully. Just because I place this charge Q in some external, some new charges voltage or field, it will have an energy of V1 into Q. Agreed on this? This charge, because of the external one, will have V1 into Q energy. Same way, this capital Q charge will also have plus V2 into Q amount of energy, V2 into Q amount of energy. Lastly, these two charges will also have an energy between both of them. So I need to add one more term over here. I need to add one more term over here. What is that last term? Potential energy between both of them. Potential energy between both of them. Hence, I will put over here K, Q, Q divided by the distance between them, whatever it is. So I'll just put Q into Q over here. This is the total potential energy of the system. That is what this statement is. Looks so scary when they do it, but when you actually think about it, it was common sense. There is nothing great. We would do it anyways. Nobody would have to teach us. We would still do it. Is that right? Is that right? Everyone understood this logic? What is R? R is the distance between them. Okay, let's see this particular question coming up on your screen. Determine the electrical potential energy of a system of two charges, this and this respectively. How much work is done to require separate infinite from each other? Suppose that same system is now placed in an external field. E is equal to A 1 by R square. A is this much. What would be the electrical energy of the configuration? Simple things first. 7 and -2 at this and this distance, -9 and +9. -9 is somewhere over here, +9 is somewhere over here. -9 you have 7 millicoulomb and this is at -2 millicoulomb at +9 coulomb. So the potential energy of 1 and 2 will be K Q1 Q2 divided by R12. K is 9 into 10 to the power 9. Q1 is 7 milli and Q2 is -2 milli, which is 10 to the power -3. Whole thing upon the distance, which is 9 plus 9, which is basically 18. Solving this, you will get a negative answer. Just check this out. That's exactly what they have done. K Q1 Q2 divided by R, but that was, I think, in centimeters. We'll convert it into meters. So minus 0.7. So the answer comes out to be minus 0.7 joules. This was also in meters. So 10 to the power -2. Yes, perfect. That is the correct answer for the first part of the problem. That is the first part of the problem, minus 0.7 joules. Now the second part of the problem says, so first part is done. First part is done. Determine the electrical potential energy. How much work is required to separate the charges infinitely away from each other? Remember, the work done to bring it from infinity to that particular point is basically the energy, change in the potential energy of the system, or basically the potential energy of that particular system. So if you do the exact reverse, the work done to take it from P to infinity will be negative potential energy of the system. So which means it is negative of minus 0.7, which will make it plus 0.7 joules. So the work done to separate it till infinity will be plus 0.7 joules, which is exactly the same answer as over here. Which is exactly the same answer as over here. Is that right, everyone? Last part. Suppose a new field is placed. Already they too have their own energy. Already these two charges have their energy. We have calculated it as negative 0.7. If you apply external field, new two terms will come. What is that total energy? We found negative 0.7. We need to find these two, add them up. I will get the total energy. That is what is the third part of the problem. So if the external field is A into 1 by r square, what do you think that potential energy will be? First of all, because E is this, we know yeah, we can find the voltage. By knowing the fact that we have to nothing but see, look at it like this. Electric field is A, what is it? A into 1 by r square. That means A by r square. Compare this with usual formula, which is K Q by r square. Our usual formula for voltage is K Q by R. So that means the potential formula will be A divided by R. Do you guys get it? How from this I got this? Usual formula of field is this. So usual formula of potential, if I compare it, KQ will become A. So it will become A by R. And what is the value of A they have given? It is given as 9 into 10 to the power 5. So the voltage will be 9 into 10 to the power 5 divided by R. So using this, I can find the voltages at both the points. What are the points? One is 0.09 and the other one is also 0.09. Distance matters. Whether it is positive or negative does not matter for potential. Yes, as long as my R is the same, R is 0.09 meters, R is 0.09 meters, the potential at this point and this point will be the same. So all they have done is multiplied voltage with the charge, and added it to the previous term. Voltage with the charge and added to the previous energy, which is negative 0.7, and they have found it out to be 49.3. That's all. That's all they have done, guys. So basically this was minus 0.7. What was this? V1 and V2, use that. A divided by R. One charge is Q1, other charge is Q2. Just add them up. A value you know, R value you know, sum them up, you will get the total answer. That's what they have done, my dear students. That's what they have done over here to get the answer. Is this absolutely clear? Everyone with me? So if you want, I will just put it over here. Potential energy of that particular system will then be V into something plus V into something. Those V's will be the same, plus negative 0.7, which is the interaction between them. These will be basically Q1 and Q2. One will be Q1, one will be Q2. What is Q1 and Q2? Already mentioned, 7 millicoulomb and 2 millicoulomb, minus 2 millicoulomb. This V will be A divided by R, which means it is 9 into 10 to the power 5, sorry, 9 into 10 to the power 5 divided by R. R is nothing but 0.09 meters. Q1 and Q2 we already know. Q1 and Q2 we already know. This is Q1, this is Q2. This is Q1, this is Q2. Substitute it, solve it, you will get the total potential energy of the system, which comes out to be as 49.3 joules. Is that okay? Understood now how this is done? Great, perfect. Now we have reached the end of part 1. We will be doing these things in part number 2. So guys, make sure that you are obviously liking the session, you are commenting below the session, waiting for part number 2. Part 1 done, part number 2 waiting for it. I want to see the comments. Okay, only then I will take the session as early as possible, or else I will delay it, guys. Okay, you want the session to be delayed, don't comment. You want the session to happen as soon as possible, I want those comments and those likes. Okay, thank you so much. Have a great dinner. Take care. Bye bye. Hasta la vista.